Minasan, konnichiwa, Zamurai Engineer desu. Now, let us do this problem wherein we have a given function fx is equal to 9e raised to the 4x. This is the same problem when we are required to solve it, but using a different method, using FDD. Now, the same problem, but we are asked to use BDD. Okay, so at the first initial value of delta x, h is equal to 0.05. So previously on FDD, we solved the what? The true error and the absolute relative true error, and show to you how to do it. Now we will show to you how to compute the actual slopes at different values of h, and also compute or calculate the corresponding approximate error and the absolute relative approximate error. So this one, this is the approximate error, and this is the absolute relative approximate error. This is now in terms of percent. Relative because this is in terms of percent. Okay. So relative approximate error. So we will do this so that you will have an idea how to do this. You already know an idea how to do this, and now actual application in a problem, how to do this. Okay, so let's prepare your pen, paper, and calculator, and also please screenshot this table, because our calculation we have to confirm if we are making the correct answer. Okay, so let us do this. So we will solve this using backward. So excuse. So let us share the calculator. Open your calculator, please. Okay. So here we have the value for the correct. We have the correct value of slope that is equal to 80.119 or 80.12. Okay, that's the correct value of correct, meaning using calculus. But now we have to estimate, approximate it, and show you that we can estimate it as near as possible to this value. Okay, so let us proceed. First, let us evaluate by backward. Backward meaning fx minus fx minus delta x. Okay, so that is how we do this. So fx therefore is just substitute 9 times e to the 4th power. What is x? X is 0.2. Okay, x is 0.2. And minus fx minus delta x. Okay, so again we have what? 9 minus 9 e to the 4 times what is x minus delta x? X is 0.2 minus the initial value of delta x is 0.05. So 0.2 minus 0.05, that is 0.15. So times 0.15. Because 0.2 minus 0.05, that is 0.15. Okay? So, and this would be our numerator. And what is our denominator? Delta x, which is h, which is 0.05. That is our value. And therefore, our answer, our first answer, our initial approximation is equal to 72.62. You can check it on the table. If you screenshot our given table. So 72.61598 actually exactly the same. Okay. Same. So we can calculate the true error and the absolute relative true error. But just what I've said, we would like to calculate the approximate error instead. Since we are going to calculate approximate error is current approximation minus previous approximation. We do not have two approximation right now. We only have one. So we cannot yet use or we cannot yet compute the approximate error. Okay? We need two values. We need current approximation and previous approximation. We only have current approximation. We don't have previous because this is the first time. So let's go to the next. Because we are going to the next, our what? Delta x should become smaller because we divide by 2. So 0.05 divided by 2, that is 0.025. Okay. So actually, we can go back here. Okay, we can actually go back here. The same equation. Okay, fx, but now the same value of x is minus 0.2 minus 0.025. 0.2 minus that is how much? So we don't need to. We can just use a parenthesis that is 0.2 minus 0.025. Okay, so and again 0.025. We have 0.025. The same equation. Okay, so same equation. Okay, I will backtrack. Okay. So let's start with parentheses, then the function 9 e to the 4x times x. X is 0.2, so that is value minus function of x minus delta x. So again, 9e to the 4x times this is x minus delta x is 0.025. That's delta x, 0.025. Divided by delta x, which is 0.025. So therefore, we can what? Press equal sign, and the answer is 76.24376. And if you have the given table, you can verify that this is the correct answer. Okay? Very easy, no? Very easy. We can immediately do that. Okay. Okay. I already gave you one technique. If there are repeated computation of that, what would you do? Just go back to the equation and change only the variable. Change only the variable. Just go back. We can still use the same equation and change the variable. What is the third one? We have the second value. Okay. What is the third value? Let us again have the same fx. We have the same fx minus fx minus delta x. The delta x changes, so the only thing that will change is this one. This should be divided by 2. Now we can just divide by 2 this one. Just put divide by 2 here. Divide by 2. Okay. And then here put what? Put multiply by 2. Multiply by 2 here. And then divide. Okay. And then we don't need to divide 0.025 by 2 because we just multiply here. This is the division of this. Meaning we are dividing 0.025 by 2. That's why I multiply it. Okay. 0.025 is in the denominator. If you divide the denominator by 2, the 2 will go up to the numerator. That is a algebraic simplification. So just press equal sign and we have the next answer. The third answer is 78.14946. Exactly the same. We can do it all up to the bottom. Okay, you can do it all. But I will leave something so that you have something to practice on your own. Okay, so the fourth one, we have to backtrack again. Use again the same formula. Just what? Multiply, divide this by not 2, but divide this by 4. Now, this is now divide by 4. This is now multiply by 4. Okay, and then press equal sign. And the next number would be what? 79.12627. So exactly the same. Exactly the same with our tabulated value. Okay. So let us do the next one. So 4 times 2, that is 8. Let's put 8 there. 4 times 2 is 8. And then press equal sign. The next number would be 79.62081. Exactly the same. Okay. So just go back here. So I already give you an idea how to use your calculator efficiently. Okay. I will give you some more later. Step by step. I will give you step by step. I will not give you the shortcut method right now because what will happen to you? You will not you will not do the long cut. You will use the shortcut always. So how about the long cut? So 8 times 2 is 16. So just put 16 here and 16 here. And therefore, 16. Therefore, press equal sign. The next result would be 79.86962. Exactly the same. Okay. So again, let us go to the next. 16 times 2, that is 32. So put the 32 there. And then put the 32 here. And then press equal sign. The next result would be 79.99442. Exactly the same. Next, it's better to, so 32 times 2, that is 64. Okay, 64. Here also 64. And then press equal sign. You will notice that we have what? Result 80.05691. And the correct value is what? 80.112. So 80.056. So it's now very near. It's now very near. We started from what? 72.6. We started from 72.6. We are now very near to the actual value. Okay. So I will not proceed further. The rest of the values from the table is your practice. Practice it and use that as your comment. And therefore, I would be able to check. Okay. So what about computing approximate error? So for approximate error, we have what? We have the current approximation minus the previous approximation. So for the first approximate error, the current approximation is 76.2424376 and minus the initial, the first approximation or the previous approximation, which is 72.61598. That is how we compute approximation error. Press equal sign. The value is 3.62778. Okay. You can check. That is the correct value. Now, we have the approximate error. If we divide this by the current, the current value is 76.24376. We press the equal sign. This is the result, but since we would like the result to be in percent, multiply by 100. This is 1, 2. So let us multiply by 100 to get an answer in percent. Okay. And therefore the answer is 4.7581%. So that is our absolute relative approximate error. Okay. And that is equal to the value given in the table. I will again, it's very simple matter to calculate approximate error because it is just what? The difference of present approximation minus previous approximation. Okay, the next one. What is the present approximation? 78. 78.1414946. That is the present approximation. Minus the previous approximation, which is 76.24376. The answer would be 1.9057. Okay, that is the answer. And that is correct from our table. Now, the corresponding absolute relative approximate error. So this should be divided. This should be multiplied by 100 because we want our answer to be in percent. Then divide by the present approximation, that is 78.14946. Then press equal sign. The value is 2.43853. Okay, so it is correct. So therefore, that is how you calculate approximate error and absolute relative approximate error. So I already explained how to do it. Please complete the table by practicing on your own. Just do it yourself. Okay? And if you have any question, please use our comment section below, and we'll try to get back on you. So let us continue with our presentation of example. So from that computation, we can plot the result of what? The first derivative in terms of number of times the step size is half. How many times the step size is half? Meaning the step size is divided by 2. How many times? So this is given here. 2 times, 3 times, 4 times, 5 times, and so on. So we have this type of graph. Okay. Effect of step size on approximate error. We are talking of approximate error in this diagram. Okay. So from the table, we can plot these points, and after plotting the points, you have to what? You have to connect the dots. Okay, connecting the dots. And then the effect of step size on absolute relative approximation error. Okay. So this one. That is how it's very clear that there is a trend going to 0 value. The absolute relative approximate error is going to 0, approaching 0. Previous slide here. So approximate error is also having the same trend of exponentially going back to 0. But here, the value is going to what? About 80, because it is in between 85-75. So in between 85-75, about 80. And actually the answer is what? We already know the answer. The answer is actually 80.12. Okay, so that's why it is about 80. Okay, so how about effect of step size on least number of significant digits? So we'll give more details on that on the next module. Okay. So effect of step size on true error. We already know this from the previous module. Okay, almost exponential and approaching zero. Exponential and approaching zero, also for absolute relative to error. Okay, so any question? Any question? If you have none, thank you for your time. Again, this is Dr. DrEYPEI, Teaching Engineering for Nation Building.